So, how many people have joined yet? Okay, people are trickling in, so we can start the lecture today. So, last time we talked about the process API and the fork system call, wait system call, and exec system call. And today we'll look at another feature of the operating system that makes possible for it to do time sharing. Okay. So today's topic is going to be LDE or limited direct execution. Okay. Let's change. Okay. So let's try to see why this is required, and I mean, what are the problems that the operating system might face, for which it might have to come up with some answers. Okay, so what we have seen is that the operating system wants to virtualize the CPU. Right? So what does that mean? That I mean, by doing that, what is the operating system trying to achieve? It is trying to share the CPU among different processes. Okay. So there are two main challenges. So first is performance, and the other one is control. So what is the performance challenge? So the performance challenge is that it should not. Why is it taking me from the input center? Okay. So what is the performance challenge? That there should not be too much overhead, right? So operating system runs the process, or it allows the process to run, or whatever this happens in this bookkeeping or in this management. There should not be too much, like the process, whatever time it takes, the total time taken should not be too much, like as compared to that. And what is control? A process should not, like, no undesired, like undesired actions allowed from a process. Like a process should not be able to claim the whole machine, or or go like kill other processes and so on. Okay. Okay. So cool. Now, so how does the question? So how does the OS come up with these challenges? So the central question for today, let's say, is going to be how to virtualize the CPU efficiently while maintaining control. Okay. So that is the question we'll answer in today's lecture. Okay. Good. So for this, both hardware and we'll see that the, okay, let me make it slightly thicker. Yeah, this might be better for you. The OS will need some support from hardware to achieve this. Okay, good. So that's where the limited direct execution thing comes in. So what does it mean? So let's look at the term in slightly more detail. So what is direct execution? So direct execution is, it just means that the program runs on the CPU directly. Okay. So that means that it's not that the program sends some signal to the OS, and for every instruction it has to ask the OS to do the thing for the program. So the program runs on the CPU directly. Okay. So this is like the most efficient way to run a program. Why? Because then there is no overhead. The program is directly executing on a CPU. So whatever it's running time, or it is taking as much time as it would take in the best possible case, because it is running directly on the CPU, right? So this is an efficient way. Okay, so as we saw earlier, if the OS wants to run a program in this case, right? So what it needed to do, create an entry in process list, allocate memory, load the program from the disk, or load instruction, that is. And then jump to the entry point of the current program. So usually it's the main function. And finally start executing the program. Right? So this is a simple approach. And but then there are still the questions that we discussed earlier, that how does the OS stop a program from doing something unwanted? Okay. And that's where the limited parts come in. So we have these two things. One is called direct execution, and one is limited part. That means that the process will have limited control, and we'll see how this is executed. Because I mean, if the process has all the control, then OS basically cannot stop like any process from doing anything, and the OS will like basically just sit there like a library, and it can't like control things. So it needs some control, and for that it to exercise its own control, it has to like reduce the what amount of control it gives to a process, right? Okay, good. So there are two questions that will be answered. So first is actually this question, but let me write it again. How to stop from how to stop something unwanted to happen. Wanted from happening. And second question is, now it also has to achieve the whole like time sharing business, right? That it has to stop one process, it has to start another process, and so on. So that also we'll discuss how to stop a process and run another. Okay. So these are the two questions that we'll be answering. Okay, good. So answer for question number one. So let's hash. So this is going to be achieved by this thing called restricted operations. Okay. So we saw that what is direct execution? Program runs on CPU. And what was the advantage of it? It was efficient. Okay. So now to solve the question that how do we stop a process from doing something unwanted. So one thing can be that okay, so you don't let the process do anything, but then a process will become useless, right? That suppose a process wants to open a file, a process wants to take some input from a keyboard, or it wants to display something on your monitor and so on. And if you don't allow any process to do these things, then the processes themselves will be useful, right? So a process must be able to perform some input, some IO operations, some other restricted operations. So how can we do that? Without giving the process full control of the system. Okay. So now one approach can be that, or one can ask, okay, let the process do whatever it wants to do, but that is for obvious reasons. So not good, right? For obvious reasons. It can go and like kill other processes, mess up the operating system itself, go corrupt some files that it shouldn't. It can do anything. So this is not a good approach. So to solve this, there are these two modes that even earlier I have talked about in brief. So, so to solve this problem, there are two modes. So first is user mode. So this is the restricted mode. This is where a process runs. Okay. Here it cannot perform any IO or any restricted operations. In fact, if a process tries to do that, the OS will kill it. Okay, so this is the first mode, which is the user mode. And okay, good. The other one is called kernel mode. So this is the all powerful mode. Okay, so does anything that it wants to do or everything. Okay, including IO or whatever. Okay, so what should a user process do when it needs an IO? So it uses this thing called a system call. And this thing allows the kernel to extend some of its functionality carefully to the processes, carefully to the user. Okay, good. So, and then because of this, now the process can ask for IO or ask for more memory, interact with other processes, etc. which is not allowed in its own mode. So there is this system call thing with which the process does this stuff, and using that, it can perform these tasks. Okay. Okay, good. So now more into detail of how a system call works, right? So for that, the program executes an instruction called trap. Okay, so what does that do? That basically like traps the operating system now, and it basically jumps into kernel mode and simultaneously raise the privilege level. Okay, and once in the kernel mode, the OS performs the desired operation. And then when the OS finishes, it uses this other routine called return from trap. So when OS finishes, it uses return from trap instruction. And what does this instruction do? This instruction returns the control back to process. At the same time, lowers the privilege level. So, like a few lectures ago, somebody had asked that, okay, what if the like program needs to do something like IO or something, and then so the answer is that it would make this system call to the OS, which will be done via this instruction called a trap, and then the OS will perform this task and then return control back to the process, right? Okay. So also there is this thing that whenever trap is executed, the hardware must save the context of the process, right? Why? Because when return from trap happens, control can be given back to it. Give control back to the process. Good. And for giving the control back, now the process should feel like, okay, it was executing as if nothing happened. So then you switch back its context and give control back to it. So the process then again starts running on the CPU. Okay, good. And this thing actually is done on a special stack, which is not a process stack. This is actually called a kernel stack. So these context is pushed on something called a kernel stack. So the kernel maintains stack of its processes that, okay, what are the processes which are running and some information about them, like some context, okay, what were the register values, what was the program counter, and some such things, what was the process ID, etc. So then, so whenever this happens, it pushes the things on kernel stack. So on trap, push like context on kernel stack, and when return from trap, then pull or reload context from kernel stack. Okay, good. Now the question is, how does the trap know which instruction to run inside the OS? So the process has issued this instruction called some trap, and then the OS should know that okay, some request has come, and now which instruction to run for this trap. The, and why this is an issue is that the calling process should not be able to tell. So which instruction to run on a trap. Okay. And the problem with this is that the calling process should not be able to tell the OS to go to certain memory location and start executing from there. Because that will be problematic, right? Why that will be problematic? Can somebody tell? Anyone?
The process will be able to execute any code with
Sorry, say
any.
again.
The restrictions we have placed on the process, they would be useless if it were able to run anything in kernel mode.
Exactly. So if the process can tell OS to just execute from a certain memory location, then that means then the process can execute basically anything in the memory. So we don't want this, that the process should tell, but then it should still tell the OS, okay, I need something and you need to do something, right? So how does that happen? So there is this thing called a trap table. Okay. So the kernel actually sets up trap table while booting. Is someone unmuted? Please check and mute yourself if that is the case, because I can hear some disturbance for some reason. No? Cool. I'll just reduce the volume. Okay, so I was saying that the kernel sets up this thing called a trap table while booting. Okay, so just a moment, sorry. Okay, so and what is the job of this trap table? So this has to be done. This setting up has to be done in kernel mode, of course, so that no process is interfering with it. Okay, and this configures the hardware. To let it know which instructions to process on a trap request. Okay, good. So this is like, so there can be many things. So when the OS boots up, it does like what to do when hard disk interrupt happens. So interrupts are some hardware driven another kind of traps, you can say. So they are some signals which are sent from the hardware to the OS that, okay, we require your attention, something needs to be done here. So that can be done by so the keyboard, if you press something, that might generate some interrupt and so on. So like, let's say keyboard or some other device, or what to do when a program makes a system call. Okay. So these things are actually called the instructions which perform a specific trap task. They are called trap handlers. And the OS informs the hardware their location while boot up. So whenever this happens, the hardware knows what to do. Whenever a trap instruction is is given, then it knows what to do. So basically, but still, like, so how are now system calls? So system calls have these things called system call numbers. And so a user code either has to put it the system call number in some register for generating the trap instruction, or some specified location in its stack. Okay, and then what will happen? The control will be given back to the OS. The OS will run in kernel mode. It will see that, okay, this is the system call number, and what is the trap handler for this particular system call. It will go and start executing there. Okay, so the OS, so then the trap handler comes. So of course, this happens in kernel mode after the control has been transferred. And first, it examines the system call. Okay, so this should be like, this is within this. So what does the trap handler do? Examine the system call number and see if it is valid. And if so, start executing the corresponding code. Okay, good. So, so this is like, as you see, is an indirect way of telling OS what to do. And because of this, and why is this indirect? Because user process can't specify a location for the instruction to be executed. So it just gives a number, and then the OS looks at it and decides. So also, I mean, a thing to see here is that, okay, so one can ask that if the OS is looking at it and deciding anyway, then why can't it even give a memory location, right? That can be a question. That, I mean, what is the difference? The thing is that by fixing these numbers for system call beforehand, then the OS can set up the whole trap table at the boot up. And then, because now if you're doing a memory location thing, then things can get tricky. That, okay, then OS will have to see whether that memory location is in, like, the program does have access to, that memory location. That memory location can belong to some other program, and so on. So then the whole process will become more complicated, and, like, it's not very clear how to deal with that. So that is why this is a simpler and, like, more convenient way to deal with these things, with these requests. That, okay, you have these system call numbers which are fixed beforehand. When the OS boots up, it sets up this trap table that, okay, if this system call comes, then you perform this instruction, and so on, right? Good. So also this whole process that when the OS tells the hardware that, okay, which trap handler you should use for which system call, right? So that has to be done in kernel mode. Did I say that somewhere? Yeah, here. That the kernel sets up the trap table, so that thing has to be done in kernel mode, because this is a very powerful instruction that when the OS tells that, okay, which instruction to execute, because otherwise, if the process itself can tell, or any process can tell, then again it can misuse it to execute whatever code it wants to execute, right? Okay, so there are these two phases of LDE. So first is at boot time, as I said. So the kernel initiates trap table, and CPU remembers the location for trap handlers for later use. Okay, and this happens in kernel mode, of course, right? And while running a process, so that's the like second phase. So whatever, allocate memory, etc., etc. Like, okay, and then use this instruction called return from trap to give control to a process. And give, of course, limited control to a process. And now, when the process will need it, it will execute trap instruction to give the control back to OS. And this can happen like multiple times. And then finally, the process then again return from trap, etc. And then process will exit by the exit system call. And after that, now the process is done. Transfer control back to OS, who will do the cleanup. It will like free the memory, etc., etc. Okay. So this is the part about limited direct execution, and so this was the first question. That okay, how do we allow processes to have uh, some to perform some tasks which are like input output tasks or anything like that, and but still not giving complete control to a process to do this. Okay, so any questions about this part? No questions?
How,
Yeah.
how is this? How are some operations restricted since the code is running directly on the CPU?
Okay, so there is basically a bit which just tells that okay whether the like it is in kernel mode or whether it is in user mode, and that bit will like signal that okay now these operations cannot be run and so on. So whenever a system call happens, the bit will be switched to one. Let's say if one is kernel mode and zero is user mode, and then now certain operations can be performed.
But says like suppose the process has access to its memory, right? So if it says store like in the code it says store something to some memory address. So does the CPU check if that memory address belongs to that process, or does the OS do that?
So you're saying that if the program is running on its own, so exactly. So now program wants to access some memory location. So the memory location it will be done at hardware part. Okay, so that okay now if the program wants to access some memory which is not in its own like memory block, then the hardware will raise an interrupt or a trap, and then the OS will come and see that okay, this process is trying to do something illegal, and it will like whatever kill it or something.
Okay, thanks.
Okay, good. Any other question? Okay, good. So now the second question that we had was okay, how to stop one process and run another. So till now we have only seen that okay, how do we run one process in a controlled manner, but the CPU also needs to do time sharing, right? So solution to question number two, that is switching between processes, right? So as I said, we want to do time sharing. So we have to switch between processes. So how do we do that? I mean, so by definition, if a process is, and what is the difficulty? Let's see what is the difficulty. So if a process is running in the direct execution thing, so by definition, then the OS is not running because the process is running. So if the OS is not running, then how does it do anything? Like the OS is not there on the CPU. It's the process which is being executed. So the question becomes that how to take the control back. Okay. So the first one is called first one is a non-preemptive approach, which is a cooperative approach. It is called. So so basically, in this, OS trusts the processes. Like, okay, you are good guys. You are not going to do something illegal. And I mean, if you do something illegal, maybe I can manage that. But I trust you to not take too much time and give control back after some time to me. Okay. So here, OS trusts the processes to behave reasonably. And what is one of these reasonable behaviors is give control back to the OS after some time using a system call. So OS basically just waits for a system call. Okay, and an example of this was yield system call, which like some operating systems used to have this call, and this would basically just transfer control back to the OS. And of course, the control gets transferred back to the OS when something illegal is happening. Because then, of course, some trap or system call will be generated, and then the control will get transferred to us. And like some memory error happens, or some division by zero happens. So control also get transferred. Okay. Okay. And in all these situations, generate a trap to the OS and return control back to CPU, to the OS. So now, can somebody tell what is the problem with this approach? With the cooperative approach or non-preemptive approach?
The process can choose to not give control back.
Exactly. So the process is executing, and it will just, like, not give control back, or even so. Another problem is that, I mean, even if the process is trying to be like, okay, I'll not do such things, such malicious things, and so on. But what if the writer of the process is not very careful, and the person who has written the program, he has put an infinite loop without knowing. And now the process just goes into infinite loop, even if it intends to like transfer the control back after, like, whatever. But now there is an infinite loop. It just keeps going there, and there is no way for the OS to gain control back of the CPU, right? So what if process decides not to give the control back? Or infinite loops. Okay? So now it turns out that in these cases, OS needs some help of hardware. It cannot, because since it is not running on the system, so that's where solution two comes, which is called preemptive or non-cooperative approach. And here OS takes help of the hardware. Why? Because if it does not, then there's nothing it can do to prevent such things from happening, right? So in these cases, the OS now will take some help of the hardware, and that is the central question that we try to solve in this part, which is how to regain control of CPU in a non-cooperative mode. And the answer to this question is timer interrupt. Okay. So all the OSs, they have a timer device, right? So what does the timer device do? It raises an interrupt after some time, or some fixed time, or some fixed number of steps. Okay, and when the interrupt is raised, what happens? It basically it looks like a system call. Then the interrupt is raised, the process is halted, and the control is transferred back to the CPU. Sorry, back to the OS. Okay. And then the OS runs on the CPU, right? So this is how now now an operating system can stop a process, right? So this can be used to and start another. So again, like before, so as I said, this will behave just like a system call. So whenever this timer interrupt happens, then the OS must save the, or I mean, the OS must inform the hardware what to do in case of this happens. So whenever, or let's just say this way. The hardware should know what to do in case of timer interrupts. So again, just like before, OS lets the hardware know at the time of the boot. That okay, whenever the timer interrupt comes, you can go to this instruction, and that thing is performed at the time of the boot. Okay, and also at the time of the boot, OS also starts the clock, the timer clock. Okay? And now the OS can feel safe that okay, what will happen is that after a certain time, there will be an interrupt, a timer interrupt, and then the control will be transferred back to me. So this is fine. Okay. And if the OS wants, it can turn off the timer also. But of course, turning off the timer is going to be a privileged instruction because otherwise a process can just turn off the timer and then it doesn't have to give the control back. So this can only be performed in kernel mode, of course. Okay. And as I said, the hardware needs to store the context of the current process. So that when return from trap happens, then the control is given back. All right. Okay, good. And this is just like so a timer interrupt is the stuff that happens is just like a system call. Okay. So and of course, where store the context? This is done at on the kernel stack. Good. So this is similar. Now the thing is that okay, this happened that a timer interrupt came, then the OS takes control back, and now it needs to decide, okay, do I want to run this process or do I want to run another process, right? So OS needs to decide whether to continue this process or run another. And that will be, or that is done by the scheduler that we'll see in, I think, next lecture. So this decision is taken by this thing called a scheduler. That is done by a scheduler. And we'll see this in more detail in next lecture. Okay. But suppose now the OS decided that, okay, I want to run a new process, right? So okay. So then it has a low level code for context switch. Okay, so this context switch is done by the OS. Okay, so there are these. This is a certain thing that whenever a trap instruction or a system call is made by the process, and then the hardware saves the context of the process on the kernel stack, right? But this is a different thing. Here, the context switching is done by the OS. So the OS saves the context of the process on the kernel stack. Okay, so there can be these two kind of stacks. One can be for hardware performed context savings, and then the other can be for these OS performed things, right? So basically, OS, what will it do? The OS save registers of current process on kernel stack. Okay.
But when the timer interrupt was raised, the hardware already saved that context on the kernel stack. So why does the OS also have to do that?
Because so what happens is that even after the hardware saves the context, the OS might decide. So the OS does not know at that point that okay, what is the process trying to do. So at that point, it just looks at it like a system call. Okay, so what happens is that now the process might have asked for something from the OS, and then the OS will save some or it will still have some data in its register about that particular process which was just like interrupted by the timer. But now if the OS wants to perform a context switch, then it completely now wants to remove that process from its, like, as if like this was never running, and now it wants another process to come in. So then it will have, as I said, so let me just say this current process on kernel stack, and then I'll come to this in just a moment. Okay. So so save registers of current process on kernel stack, and then restore registers of the next to be executed process, again from kernel stack. Okay. So now when return from trap will happen, control goes to the correct process. Okay. Good. So, all right. So this is generally some assembly code which performs this. And basically this meaning context switch. And as you would expect, it, like, saves the general purpose registers, program counter, okay, and yeah, some new, and then restore all these for the new process when this happens. So basically when the OS performs this call, code, or executes the performs this task, it enters the uh, it enters in it enters in the context of new process, sorry, the old process, and comes out of in the context of the other process. So let's look at the difference that I was talking about, the question that it asked. So see, so there are these hardware context switches that happen. So once you go from user mode to kernel mode, okay. So here now, of course, the as I said, during a system call or for a timer interrupt and so on. In this case, the hardware saves the context on kernel stack. Okay. Now in kernel mode, the context of one process, and from there now inside kernel mode only, we want to go to context of another process. So this task is performed by the OS. Okay, so as I said that, so these are the two kinds of context switches that happen. One is while going from user mode to kernel mode, or again from kernel mode to user mode, or back. And they are performed by the hardware, which will just pull the things from the for the trap or return from trap instructions. But now the computer is already in the kernel mode, and then the kernel wants to switch between certain processes, right? So then it has to perform a different kind of context switch, which will be performed by the OS, and where again it is very similar that okay, the registers will be saved and so on. But for example, as I said just now, that now when the return from trap is going to happen after this, after the context switch, then the return from trap should take to the new process and not to the old one, right? So this is a different kind of context switch. So the earlier one would not have altered the position where return from trap will take it to. But this context switch will alter the return from trap instruction as well. The OS driven context switch. Does that answer your question, Arpit?
Yes, sir.
Okay. So this is one subtlety that is there, and you can in the book there is like clearer example of which instructions are executed, and you can have a look at that. And I'm covering whatever is there in the book, but of course I would encourage you to go read it, and I think after the lecture it should be quite easy to do that. And now there are some what to say there are some issues with all this. So we saw these two things. One was how to do limited execution, and the other was how to do context switching. But there are some problems like what happens when an interrupt is generated during a system call. So already the OS is doing something. It is handling some trap, or it is doing a system call. So it is already in the kernel mode, and now an interrupt comes. So we have not really talked about it. That okay, now how to do this, how the context switching will work, what to save, and so on. So such things can happen. The OS might just ignore these interrupts. So there can be two ways to deal with this. So maybe just don't allow interrupts when some interrupt is being handled already. Or maybe just ignore. But if you ignore, then some other problems can come, that some interrupts can go missing, and that might not be very good. So all these problems are basically related to concurrency, that okay, at the same time many things are happening. So we'll discuss this in the later part of the course. And yeah, so I guess that's for today. So we saw a few things, that what is limited direct execution. So direct execution means the process basically runs on the CPU directly, but then the OS has to limit that execution, that what a process can do, because if a process is allowed everything that it can do, then there will be some problems that you don't want to happen, like accessing other process memories, accessing the OS instructions, and doing something bad. So for that, there is this user mode and kernel mode. And from the user mode, when the process wants to go to kernel mode, it or whenever the process wants to do something like IO or anything like that, it issues system call, and then the system call will be handled by the OS, and it has to be careful that on what to do on that system call and how that thing is achieved using the trap tables and so on. So we saw all that, and then we also saw that okay, how does the OS switch between different processes, and like what it does when it switches between different processes. So any questions about whatever has been done today? Any questions, anything? Otherwise, like, yeah.
So will you please upload this lecture on Moodle?
Sorry, there is a lot of like disturbance, I guess. Say it again, please.
Will you please upload this lecture on Moodle?
Later. Was anyone else able to get the question, or like, or it was?
So he was asking when will you upload the slides on Moodle or lecture on Moodle?
Slides from the lecture. I mean, these are not really slides. These are like some notes, and I mean, you have the recording anyway on like on this thing, on this. So I don't know whether I plan to upload the slides, because these are mostly stuff from the books, from the book. So yeah, I mean, will that? Yeah, these are not slides actually. So these are just my, I write on like a person writes on the board. I'm writing here. So I don't think I'm like, yeah, I'm planning to upload it.
Okay, so I mean he was asking that.
Yeah, yeah, okay, okay. So yeah, I hope that. That's okay. So this is like, yeah, just writing on the board. This is not these are not slides. And actually, the like whatever I write also, it is mostly like, just from the book. So and I don't write complete sentences and so on. So if you just go through the book, that is going to be the best thing, rather than, and my writing is anyway not very good. Any other questions?
Sir.
Yeah.
This is regarding that system call portion.
Yeah.
So, at which stage is exactly the requirement for system call found out? Like, is it during at that line of the process execution, or like when is it exactly found out?
So it's a specific instruction. So now depends on the operating system and how it wants to handle it. So it can just ask the process to say that, okay, whenever you want to make a system call, you basically, this is the register where you need to put this number, and then you need to change this particular thing, and whenever this particular like some other register, or you have to make this instruction. So now, whenever that instruction is made, now like the register value will be read, and then a signal will be generated, which will then increase the like privilege level and so on. So when exactly is it found out is when the process runs a specific instruction, and that might vary from OS to OS, that what that instruction is. Like the trap instruction, it's a system call. So then, so before doing that, the process has to set up that, okay, which system call I'm going to run, and then that is going to be pre-specified by the OS, that how it is to be done, and then the process will do it.
Okay, so it's at that particular line of the process, right? Not beforehand.
A particular line of the process. Yeah, I mean, whenever it calls the, like, if you are looking at a high level code, then it is just when the system call is made. But if you're trying to go into like exact details, that okay, what happens at the machine level and so on, then that line will be broken into many lines of assembly code, which will then as I said, put something into some registers and then try to perform some operation at which instance the control will be transferred back to the OS.
Okay, sir. Thank you.
Any other questions? Okay, cool then. See you guys on Monday. Thank you everyone for coming today. And yeah, see you on Monday, 9:30. Thank you.